Okay, so please notice on the right board, the board on the right hand side, you know it's on due dates. What work is 4, 5, and 3. I'll release it tonight. I mean, I think it's already released, but I'll just have to open it for you. And then this is your plan for the week, I guess. I guess a heavy week, but you should expect all the following weeks to be similar. Okay? So, let's continue. What work 2 is due tomorrow, right? So I will extend this to Saturday, if that's fine, okay? Or you guys did it already? Okay. Okay, that's Saturday. I'll extend it to Saturday, and then, yeah, okay. Great. So let's continue where we left off yesterday. Let us remind ourselves of the definition of a limit. And the quiz will be up. The quiz will be up tonight. You may not be able to do it all, okay? You may be able to do the first. So the quiz will be just a replica of the midterm, okay? It will be the same thing as the midterm. So the thing that you usually like, the same things with number change. Well, not number change, but series, for example. I'll give you a sample midterm that you're going to have to do in 50 minutes, but the quiz is open time, okay? So you don't have to time yourself during the quiz. It's going to be a multiple choice, and although the midterm is not a multiple choice, but just to grade it, to have it graded easily, I'll put it as a multiple choice, and you have only one attempt. Okay, so you can submit anytime you want, but just please be sure that when you submit, it's the final submission. Okay? Yeah.
Is it through my course or just through web?
I'll check. Okay. I think you'll get a notification if it's on my courses, and then if it's on WebWork, you will be able to spot it. Okay? But again, you have a lot of time, so you have a few days to complete it. First, I think that's supposed to be 50 minutes. Okay? And then the rest of the WebWorks, 4 and 5 and 3 are due next week. Okay? And then the other week we'll start with two WebWorks and 1 quiz, maybe the week after so next week I'll release 2 WebWorks, maybe, if not 3, and then 1 quiz. Okay? Great. The limit definition. So let's recall what we have done for limits. Any questions on this? Any questions? Oh, by the way, are you attending the tutorials or not? Very good. Okay. So let's we say that the limit if every if for all epsilon positive. Anyone can remind me? There exists delta positive such that delta, I forgot here, yesterday I forgot this one. Please put it. Should be strictly bigger than 0 as well. Implies f of x minus Okay. Well, I mean, you can forget about this. That's okay. Just for the limit to be defined. And then we gave examples of stuff. So, let's give an example. Well, let's give some properties. So if the limit of fxy is equal to L, and the limit of gxy is equal to L prime, what is the limit L plus or minus L prime, right? And what is the limit of fxy times gxy? Is there L prime? What is what? What did you see? The quotient of f and g tends to L over L prime, provided that everybody provided that L prime is non-zero, right? Thank you. If L prime is non-zero. Okay? Are we good here? Any question? Any questions? No? Easy? Okay. Great. Now what is defined as, well, we did something else. Suppose that f is continuous. Or it doesn't have to be R, just L has to be the domain of f. And f is continuous at L. The limit as x y approaches AB of f of fxy is just f of x. Really, this is just generalizing the stuff of the single variable. Okay, great. What else? What else did we see? What other definition did we see? Continuity, right? So when is a function continuous? We said fxy is continuous at AB if what? If the limit, of course, f has to be defined as AB, and all of this stuff has to exist. We say that fxy is continuous at AB if what? The limit approaches AB of fxy is at AB. Now the property, proposition or properties if you will. If f and g are continuous at AB, y are continuous at AB, then f plus or minus g and f and g are continuous at AB, and f over g is continuous at AB provided GAB is different. Okay? We have seen this, and then we have moved to see examples. following limits or show they do not exist. Okay, so the first limit, I mean, this is an obvious one. Well, I mean, they don't have to be the same numbers, but. What's the first thing to do here, everybody? What's the first thing to do? Plug in. If I plug in, what do I get? This function is obviously continuous, right? X squared is continuous, and x is continuous, y is continuous. So a combination of these is obviously continuous. So what is this limit? So it's 2 squared plus 2 times minus 1. What is that? Which is 4 minus 2, which is 2. Very good. Thank you. Let's do another one. What is that? What is this limit? 0 over. What do I do? What's the first thing I do? I plug in, right? When I plug in, what do I get on top? Sine of 0, right? Sine of 0 is downstairs. What do I get? Cosine of, which is, so 0 over minus 1 is, can I define 0? What's 0 over minus 1? 0. Very good. Okay? Let's do one more. Let's do one more. Let's see. What is this? What is this? Y is 0. Square root of 0, and how did we see that? What can we do? Plug in. Very good. That's nice. Okay, what if I have can I do that? Is there anything wrong with this? What do I do here, everyone? Plug in. What do I get? Square root of. Okay, let's do a more interesting one. Okay, what is this? This is an interesting one, I think. What do we do here? What's the first thing to attempt? Plug in, right? When I plug in, what do I get? 0 over 0. Can I say what 0 over 0 is? No. In calculus 1, what did we do? We tried to, well, okay, we tried to, first, before looking at it, we tried to simplify, right? So let's factor this. Notice that you can factor this, no? Try to factor this. Try to factor an x here. What do you get? 2x minus y, right? And downstairs, 2x plus y and 2x minus y. Right? What happens right now? What can I cancel? The 2x minus y. Then can I plug in or not? I can plug them in, right? Can I plug in now? Plug again. 1/2 plus 2. Okay? Are we good here? Great. Are we good? Any questions? Questions? Great. Let's move on. Let's do more. Those are a bit technical. Have you guys seen, are you guys comfortable with polar coordinates or not? No? Okay. You know, it may help us later on. I mean, now we won't need it, of course. But let's look at this limit. What's the first thing to do? Plug in. I plug in on top. What do I get? I plug in on the bottom. Okay, I have a problem. Now what happens? What can I do? If a limit as xy approaches 0, 0 of f of x exists, what did we see yesterday? Along any path x and y approach 0, my limit should still give me the same answers, right? So suppose this limit is finite. Let's say it's equal to 1. If x and y approaches 0 through this line, while y is equal to x, what should it give me? What should it give me? Say this limit is 1, for example. And if x and y go to 0 along this line. So if x is equal to y and x goes to 0, what answer should it give me? 1, right? Agree or not? Great. So if I start with y equal x, what happens? While y is equal to x sin xy, what happens here? This is just the limit. As xy goes to 0, 0, y is equal to x, right? Of sine x squared over 2x squared, right? Agree or not? If you take y is equal to x, and then you take x to 0, that's what you get. Now what is this limit? What is this limit? Very good. Why is it 1/2? Anyone can help me out? It's sine t over t as t approaches 0, right? That is 1/2. Agree or not? Everybody, do we agree with this? Any questions on this part? Yes, sir.
We do this only when x is 0 and y is 0, or whenever y is equal to x?
No, so if y is equal to x, you want to approach 0, 0, right? What's one way of approaching 0, 0? You go along y is equal to x, right? So if you place y equal to x, where does x go to?
Y?
0.
0.
Yes, x is equal to y, and both go to 0.
But do we only do this when it's 0, 0, or
Well, if it's 1, 1, for example, you can do a line like this, right? Y is equal to, if it's 1, 0, say, y is equal to x minus 1, and you take x to 1, right? Your line should converge to the point. Okay? Great. Awesome. Then, what else do we do? What other choice could I put? So along one path, it's equal to 1/2. What's another path I can do? Y is equal to? Sure, let's do that. Now, if this limit gives me something other than 1/2, what can I say? If x and y go to 0, 0 along the path y equal to x. If this limit gives me another number than 1/2, what can I say about this limit? Does not exist. Very good. So the limit as xy goes to 0, along the path y is equal to 2x sine xy over x squared plus y squared. What do you get? Of course, if y is equal to 2x, you just take sine 2x squared over y is equal to 2x, 4x squared plus x squared, is just 5x squared, and you're just taking the limit as x goes to 0. Agree or not? Everybody, do you agree? xy goes to 0, 0. Along the line, y is equal to 2x. So it's just enough to take x to 0, y will go to 0 immediately. Right? If x goes to 0, then 2x goes to 0. We see that or not? Yeah, we see that? What is this limit?
1 over 5.
What is it?
1 over 5.
Well, let's be careful here. Close. Oh shoot, what did I say? Yeah, sine x squared, you're right. No, you're right. You're right. Sine x squared over 5x squared, which is... No, that's right. No, 2x squared. No, 2x squared. Y is 2x, right? So it's 2x squared on top, and 5x squared on the bottom. What is this limit? What is this limit? 2 over 5, you see that? Because what you need here, you need the 2x squared, you need the two of them to be the same on the bottom. Right? So, agree, everybody? Do we agree? Sine A over A as A goes to 0, what is that? Is it good? Sine A over A. You need the same one here and here. What is that? 1. 1 divided by 5 over 2, which is 2 over 5. Yes, sir?
How come you need the same one?
So, you need sine T over T, right? Okay? Fit your T to be equal to 2x squared. What is your x squared here? Your x squared becomes T over 2. Okay? Is it clear? Are we good? Are we good? Yes, sir.
I just have a question.
Yes.
When do you know it's y equals to 2x or y equals to
You just choose. You can choose y equals to 3x, for example.
and it works. Depending on...
Depends on the case, right? It's just practice. Yes, sir. No, someone else has that. Yeah.
How do you prove it does exist? You can't try every problem.
Yeah, I mean, we'll see now an example where it does exist. Yes, sir.
Well, we can just go into like x, y, like 0, 1,
xy went to,
like 0, 1.
so y is 1 and x is 0.
Yes.
So x is 1 and y is 0. What is on top? Plug in first of all.
No, but like, if you put 0, it's still leaving 0, 0.
We'll see. Okay? We'll see an example. Sure, we can say an example like that. Yeah? If it, you mean the bottom has still given me 0 over 0. Okay, what you can do is to change the variables. So set v equal y minus 1. If it, right? You can do that. But it doesn't, and then take v to be 0. If you're more comfortable working with 0, 0, then you can do a change of variable. Okay? Any questions on this? Yes, sir.
How do you know that we have to set y equals to 2x?
Choose another direction, any other direction. Y equals 10x. Okay? It's practice, usually. I mean, there is one reasoning, it's more like with polar coordinates, but I don't. If you're not comfortable with it, then just drop it. But I mean, the idea is you try. Okay? The idea is trial and error. Just try and see if you're mistaken or not. If it gives you the same answer like 25 times, then you know. You may be, you may want to prove it rigorously at the same limit. Yes?
So how do you know which one's right?
Well, you have two different answers. Does the limit exist then? No, does not exist. Someone here had a question? Someone here had raised their hand? No?
Sorry, can you repeat that last part?
Yeah, so if these two answers are different, right? So, in both these cases, x, y go to 0, 0, right? here xy goes to 0, 0, and here xy goes to 0, 0. The answer here is 2 over 5, and the answer here is 1/2. Can this limit exist? Okay? Yes? It doesn't tell you, no, because you're taking a particular path, right? Yes?
So how would we tell what the limit is using the method? Is there no way to do so?
Well, you know if the limit exists, it must be equal to 1/2, right? If it exists. Right? Well, omit this one. So say this limit exists.
Yeah.
If you really think that this limit exists, it should be equal to 1/2. But you cannot prove it rigorously because it doesn't. We'll prove things rigorously when the limit exists. Okay? Let's not worry too much about it for now. In 5 or 10 minutes, we'll worry about it. Yes, sir.
Okay, I was gonna say, like, on an exam, would you specify if there is a limit?
I will ask you the same question.
Okay.
Okay? For each of the following limits, find the following limits or show that they do not exist. Okay? Any questions? Should you do more like this? Let's see. Let's see if we can. What I want to do is are you guys comfortable with bounding stuff or not? Big or equal, small or equal? I mean, we could do it. Yes?
How many conditions do we need to test to make sure that it exists?
This doesn't show you that the limit exists, right? So suppose you got the same answer on both sides. That doesn't show you that the limit exists. Because you might still get you may still try another path where the limit is 0. Is a different number. Okay? So, you really cannot prove using this method that the limit exists. This is just to show that the limit does not exist. Along 2 different paths, it takes different values. Okay? But, yes.
But what if it's just like 5 functions and every answer is like 1 over 2? Can we say that the limit might exist?
Well, you start having, you start believing that it might exist. Okay, but that doesn't show it. Okay? You start believing that it exists. I mean, take these. Take, for example, the first example we did, right? Let's say 0, 0. Okay? What is the answer to this limit? 0, right?
Yeah.
What did you do? You plugged in. Okay? Now take the limit as y equal x. What do you get? 0, right? So you get x squared plus x squared. Take y equals 5x. So you get x squared plus 5x squared, 6x squared, and you take x to 0. Now, but that doesn't show that this is the limit. You start having suspicion. Okay, the limit might exist. But that doesn't show you that the limit exists. Okay? Is that clear?
Yep.
Yes?
What if we take y to be 1 over x, then you have x squared plus?
Y to be
Oh no.
1 over x,
No, no,
how
no.
will y go to 0,
Yeah.
right? You need them both to go to 0. Any questions? We do one more where it doesn't exist. And then we will do one where it exists. Okay. What do you want to do? Let's do something nice. So which one did we do yesterday? We did x squared, xy over x squared plus y squared. Did we do this yesterday? Xy over x squared plus y squared. Is that what we did? Let's do this again. Okay, let's do this. So limit as xy goes to 0, 0 of what they have sin xy over x squared plus y squared does not exist. Okay, now let's do one more. Let's repeat this actually. Of what? What was we have xy over x squared plus y squared. Equal, does it exist or does it exist? If you want to take 2 minutes to try it on your own, if you want to take 2 minutes, try it on your own. It's not a time to talk or to chat, it's a time to look at your notebook and, try to write it down. I mean, we did this yesterday, so. Good. For example, this is a perfect exam question, final exam question. I give you like 5 limits, and I tell you how many of these exist. Exactly 1, exactly 2, exactly 3, exactly 4, or okay? Does it exist? Do we need more time, or that's fine? We need like 30 more seconds. Okay, does it exist? Does the limit exist? Why? If I go to xy, who volunteers? Any volunteer to answer? Someone who hasn't spoken today? Yes.
If we try with y equals x,
Yeah.
we get 1/2.
You will get 1/2, so let's try that. So if y is equal to x, what do I get? Xy over x squared plus y squared. This is the same thing as the limit as x goes to 0 of x squared over 2x squared, which is 1/2. Very good, thank you. And then someone else who volunteers? Yes?
If you take x equals 2y, you get 2x.
Very good. So if I take x is equal to 2y, x is equal to 2y, as y goes to 0, right? So you're going to take y. I mean, you can take y to 0, but you have to replace. You use the substitution, so limit as y goes to 0, where are we? So x is equal to 2y, so you get 2y squared over 5y squared. So what do you get? Over 5. Very good. Does the limit exist or not?
No.
Okay. All good? Yes, sir.
Is it a coincidence that the same, because we used the same equation previously, we got the same answers, or is that somehow related?
What was it?
To the previous problem that we did, we also.
Oh no, it's unrelated. And then you could have obtained other things. Yeah, you can have obtained other things. So take y is equal to 3x, what would you obtain? If y is equal to 3x, you'll obtain 3x squared over 10x squared, right? You get 3 over 10, okay? Okay, thank you. Thank you for those who spoke. Now really this depends on the direction you're approaching, right? You can see that. This limit depends on the direction you're approaching 0, 0, right or no?
Yeah.
Okay, now I want to say something about polar coordinates, but it makes things a bit easier actually. But okay, now let's do the following one. Let's see. If you pick an example where it does exist. Well, it's not easy, but let's remind ourselves of some points that we have seen in calculus 1, and then that will easily generalize in calculus 2. So if I tell you that the limit as x approaches a of absolute value of f of x is 0. So the absolute value of f of x goes to 0 as x approaches a. What can I say about the limit as x approaches a of f of x? 0, right? You've seen that? So this is by just definition of the limit. From calc 1. Limit Right? You remember this fact from Calc 1? This is kind of the definition of the limit, allows us to prove this immediately. Okay? One way you need definition, so if the absolute value of f, yeah, I mean, this, from here to here is just definition, and from here to here is also the, right, it's more or less the definition. Or you can use the continuity of absolute value, or anything you want, okay? I mean, you know, there's a lot of circular reasoning here, but let's not worry about it. Okay? Another way to see this by the squeeze theorem, right? You know that f of x right? Right, you saw this? You saw something similar. So if this goes to 0 and this goes to 0, this thing goes to 0, right? Okay, and if this thing goes to 0, then the absolute value of 0 is also 0, okay? Wait, oh man. I thought I made silence. Okay? So if I need to show that, you've seen this in Calc 1, right? So if I want, and the same thing holds in two variables. So if I want to show something tends to 0, I can show that the absolute value of this something goes to 0, right? Agreed?
Yes.
Yeah. So let's do an example like that. Oh man. I think we have a soccer game tonight. It's not even close enough to focus. How many players are we gonna have? I hope we won't go, you know, forfeit, you know, because lack of players. But we'll see. Anyways, let's do one. So let's remind ourselves the squeeze theorem. In one variable, anybody can help me with the squeeze theorem? What are the conditions? Squeeze theorem in one variable. If f is less or equal to g, less or equal to h, right? So if f is less or equal to g, well, is less or equal to h, right? And the limit at f and the limit as x approaches a of f is equal to the limit as x approaches a to h. What is that equal to? Then what can I say? G has the same limit, right? The same thing in two dimensions. Well, if, sorry, fxy. In here, all you need them to be less or equal to each other in a neighborhood of AB, but that doesn't matter. And let's not worry about this for now. You can prove these easily. So what I want to say, AB of hxy is equal to L, then of gxy is equal to L. Okay, this is obvious, right? Yeah? Okay? Yes or no? It's clear? Okay. Great. Okay, so find there is a way to do it, and then it's faster actually if you're not comfortable with this one. But may require the use of polar coordinates. But okay. I can tell you the limit exists. Okay, if I tell you this limit exists, well, I won't tell you on an exam, but I can tell you now that this limit exists. Now, how to show that it exists? So really, you need xy to go to 0, 0 in any way, right? So plugging in values of lines, say y equals 5x or y equals x squared, will not work. I mean, it's all going to give you the same answer because this limit will exist. But showing that it actually exists may take some work. So what I want to use a squeeze theorem here. So let me bound this. And let me show that the limit of the absolute value goes to 0. If I manage to show that the limit of the absolute value goes to 0, I'm done. You agree or not? If the absolute value of this thing goes to 0, then this thing goes to 0. Agree or not? Yes or no? Okay, let's do this. Of course, when you take xy goes to 0, 0, then xy is different than 0, 0. Okay, that's clear. Right? When you take limit as x approaches a, then you can assume that x is different than a, right? That's how you do it, right? Great. Now, let's see, what do we want here? What do you think is a good bound? What do you think is a good bound? Do we agree that x squared plus y squared is bigger or equal than x squared? Strictly bigger than 0? Well, right? Then, what do you get? Try to apply this.
It's smaller than y. Because they cancel each other.
Very good. So this is strictly smaller, so here x is different than 0, right? So this is x squared y over x squared. You agree or not? Yes or no? You see that? This is less or equal to what? To the absolute value of y. Agree or not? Any questions about this? Are we comfortable with this or not? Are we good? Now, where does the absolute value of y go to if x and y go to 0? 0. 0, right? And well, of course, this is positive. This is positive over 0. So the limit as xy goes to 0, 0. Here, what do I have? Of 0 is equal to 0. And the limit as xy approaches 0, 0 of absolute value of y is equal to 0. So what can I say about the limit of the absolute value of this thing? 0. Now the limit of absolute value of f goes to 0, so the limit of f is also 0. Agree or not? Are we good here? Any questions? Any questions? Yes, sir.
Instead of having x squared or x squared, I just have the x squared y being greater than x squared y over x squared y. Yeah, so
Sorry, could you repeat?
instead of having that, could I have another bound where x squared y, just x squared y?
So you want to put a y here?
No, no y, just x squared y times y.
Well, is this bigger than 1? Right? So what do you want to say? You want to say that x squared y over x squared plus y squared is less than x squared y? Is this true? Say x squared plus y squared is small, right? Then it's not true. Okay. Of course, what would be interesting is to see what if instead of the x squared, I put the y squared here. So I get x squared over y. You have x squared over y. If I had picked the wrong bound, you get x squared over y. Now you expect x squared over y to diverge. But does that tell me anything about this? Does the squeeze theorem tell you anything if the upper bound diverges? Okay? So you have to choose the right bound. Now, there is a way that can help you. It's using polar coordinates, but that's we can omit that if you wish. I don't think the book does it, but you have to be careful when you use it. Okay, let's do one more. Now, really it's the same thing. Okay, it's not very different. Do you want to take a minute to do it? Sure. You want to take a minute to do it? Try it and see what you get. Yes?
Is there a reason you take the absolute value and the lower bound? Zero.
Pardon me?
Is there a reason you take the absolute value?
Yeah, that's that you can apply the squeeze theorem. Or really by definition of the limit. Definition of the limit really. If you show that the absolute value minus 0 goes to 0, then the thing inside goes to 0. This is by definition of the limit. But yeah, sure. Take the absolute value by squeeze. If both go to 0, then the absolute value goes to 0. If the absolute value goes to 0, then the function itself goes to 0. Okay? You've seen this stuff before, no? Yeah, you've seen this in Calc 1. No? Yes? No, you haven't seen? Okay. No? Okay. What is it? What is the limit? What is the answer here? 0. Right? We see that? Is that equal to 1? You can pick, you can choose the one you wish, right? So let's say it's equal, here is yes, sir.
Can we do here x squared times y minus 1 squared over y minus 1 squared?
Yeah, sure. Then the x squared will have an x squared, right? Sure. Okay. If xy goes to 0, 1, where does this go? Y minus 1 squared, what happens if y goes to 1? 0. What happens to this? 0. So what happens to being in the middle? 0. So what happens to this? 0. Okay, are we good? Since and hence the limit of the thing in the middle in absolute values. Okay, great. I don't know if we should do more examples or. More examples, or that's fine? I think it's fine. It's fine? Yeah. Great. Any questions on this stuff? Any question on this stuff? Yes, sir.
Do you always compare with the denominator?
With the?
Denominator.
What do you mean?
Like with the example above it, it said x squared plus y squared is less than x squared. So we use x squared.
Yeah, of course. You need to bound this. Exactly. You need to bound.
Compare with the denominator.
If the squeeze idea works, yeah. Okay.
And why didn't the idea of like doing lines like y equals x and y equals 2x giving us the same answer, not proof that they didn't exist?
Because you need to go to what about you go y equals 5x?
So we don't get the same answer.
What if you get the same? What if you don't get the same answer? Do you have any guarantee?
It doesn't exist, right?
Sure, but you say you take y equal x and y equal 2x and you take them both to 0 and you get the same answer. Okay? Does it guarantee that y equal 5x will give you the same answer?
Oh, because you have to try multiple. Yeah, because
Does it guarantee you that if you take y equal, let's say, 5x squared, does it guarantee it exactly? But here, you're guaranteed. Okay? Great. Any questions? Okay. Now we're going to move on to partial differentiation. If you want, we can do a few more. I mean, we have time. I think we have time. If you want, we can do a few more. We do a few more. Let's do a few more. Oh, okay. Of what? Let's see. Look, I have here 2x squared plus 5. Ah. Yes, sir.
But at first we don't know that the limit exists or does not exist. So we first try to do the line. Then if they match, we do the squeeze here, right?
Sure. Yeah, you can try. You can try whatever you want. Okay. I mean, usually there is a way that you're able to spot it immediately, but it involves polar. I don't want to say immediately. You still have to be careful, but there are ways where you can start doubting. You know, it gives you a very educated guess. If you want, we can try with something with polar coordinates. But yeah, okay. It can give you bounds easier, just because cosine and sine are less than an absolute value. So if the bounds work out, then you can bound it easier, but an easier way, I guess. But yeah, sure, let's not do that. Just involve some bounds, but you still have to be careful. You cannot just apply things immediately. So, what is this limit? Does it exist or not? It doesn't exist.
Should we ever check 0 minus and 0 plus after the transform?
Well, what is minus and what is plus?
Here it doesn't matter because they're squared to the form.
No, but what is 0 minus and what is 0 plus?
Negative 0.0001.
Sure, but you're going to a point, right? You're going to a point in the plane, right? What is?
The direction of
So instead of 0 minus 0 plus, for example, is a direction. That's one, but it's not the only way, right? It can. So say it goes to 0, 0 along this line.
Yeah.
That's sort of a restriction that you're putting. Great. Now, what did we try here? Did we try it or not? So what did you try first? Y equal x. What did you obtain? If y is equal to x, so we obtained x to the fourth over 3x to the fourth. We obtained 1/3. What's another way? What's another one we did?
Y equals 2x.
Y equal to x. Sure. So we obtained 4x to the fourth over 18 x to the fourth. So you get 4 over 18, 2 over 9. Is that right? Is that what we got? Yes or no? Is that what we got? So does the limit exist? No. Okay. Y is equal to x thing. Of 2x to the fourth over, sorry, x to the fourth over 3, right? You get 1/5. I mean, you can try another one, right? If you try y equals 0 for but anyways, that's not confusing. Whether you say y is equal to 2x here, y is equal to 2x, so you get 4x squared, 4x to the fourth, right? 4x to the fourth over 16, 18, x to the fourth, which is 2 over 9. Okay? So the limit does not exist. Okay. Let's see if there are more things in the book. I don't think so. Yeah, I don't. You could do one more if you wish, but. We do one more? Yes, sir. Pardon me? Here? Here I did not use the squeeze theorem. Why would, if the two limits are different, why would I use it? Right? The limit does not exist. Pardon me?
We use the squeeze term first. So we have to squeeze term always second.
In this case?
Yeah.
So let's try to use the squeeze theorem. So you want to take the absolute value thing, right? So which one do you suggest? Is less or equal than 2x to the fourth, for example? Blows away, right? So it doesn't tell you what happened. Okay? Okay, any more questions? Let's try one more. We can try one more.
Could he always take y as a function of x and x as a function of y?
Usually, yeah. Or x is one, yeah. But as long as they both go to 0, yeah.
And we can take some.
So y is equal to 0 and x goes to 0, yeah. But it's a bit confusing.
You can take x to be a function, a constant.
Yeah.
Although
Well, I mean, what constant should it be here in that case?
I mean, like in general, like wouldn't it fail the vertical line test?
No, here you can take x to be 0, right? Fix x to be 0, and y different than 0, but goes to 0.
Okay.
With perfect rule.
But are you allowed to say that x is like, because I'm imagining on the xy plane, for it to be a function, x has to, it has to pass the vertical line test.
There is no the vertical line test works in one variable, right? Here, what's a function? It's a rule that assigns for each pair xy one value fxy, right? So 1, 2 and 1, 3, they're not the same pair. Okay? Yes, sir.
So am I correct that the idea behind what you're saying is you first try with different variables, and if the numbers that you get, the two limits are the same, then you go into using the squeeze theorem to determine what.
I don't want to say that, but it's not a rule, right? So, but if you have 2 or 3 trials that give you the same limit, then you know you could get the squeeze theorem. Now there is a way to be able to spot immediately, but it involves polar coordinates. Okay, so
But as a generalization, yeah.
pardon me.
As a generalization, yeah.
Well, I mean, do you want to try something with polar coordinates?
Sure.
It's quick. It's quick, but again, don't make up your own rules. Okay, don't make up your own rules. Okay, because things can go crazy sometimes if you try to do your own rules. Okay, let's pick one example. Y cubed over x squared plus y squared. And I want this as xy goes to 0, 0. Okay? You can do it with the squeeze theorem here, right? Because this is going to be less than y in absolute value. Right? You see that? We see that? Now, what if you try something without the squeeze theorem? The idea is that you know that you can write x, so any point in the plane can be written as x is equal to r equals theta, r sine theta, right? This is say xy, and this is theta. You agree?
Yeah.
Have you seen this before? This is a trig circle, but with radius r. And r is just root of x squared plus y squared. Right? R is the distance from the point xy to the origin. You've seen this before? Yeah? You've seen this in linear algebra maybe? Yeah? Okay. Now, why is r sine theta? Agree or not? Let me just replace this. What do you get? You get r cubed sine theta over r squared. Agreed? So you get r sine theta. Agreed?
You don't cube the sign?
Sine cube, sorry. Thank you. Thank you. Now in absolute value, this is still less than r, right? Because sine is less than 1. So really, okay. Is it? Yeah, I think it is. Yes.
Are we expected to be able to do this in the
No,
midterm
no,
or
no,
final?
no. This R cube is this polar business. Okay, but this is just a way, for example, right? Is it? I don't know why though. Let's see. But it's weird, isn't it? No, it's not. It's not weird. But yeah, it's not weird. But you see that? Anyway, now if you take xy to 0, then r goes to 0. So this one will go to 0. Okay. Okay. Great. Otherwise, you can try the squeeze theorem and it will work. Let's now try derivatives, partial derivatives. Anyway, this was a good discussion. So I will not examine you on this on the midterm, okay? This on the midterm you won't have.
No.
This on the midterm you won't have.
What do you mean by this?
This limit business on the midterm you won't have.
So up until Taylor series and Maclaurin.
No. I will. The next chapter, this one partial differentiation will be on the midterm. Okay, but this limit business won't be. Okay, unless you want me to put it, I don't mind. Okay, it's easy for me.
But it could be on the final, right?
It could be on the final. Yeah. It could be on the final. Okay, great. Now partial derivatives. Partial derivatives. Now, okay, so this limit business won't be on the midterm. So for the midterm, you won't have to study it, but for the final, I think you'll have one question. Okay, I think you'll have one question in the final. Great. Partial derivatives. How did we motivate derivatives in calculus 1? We had a curve y equal f of x, right? And what did we do? How did you motivate the derivative? I picked the point x0 here. I'll let this make bigger. And I picked the point x0 plus h. And now what did we look at?
We did f of x0 plus h minus f of x0 over x0 plus h minus x.
Very good. Minus x0. What is that? What does that do?
And we have to do the limit as h tends to 0.
Sure. But what does that give me? What is this? This is
That's
just
the equation of
Round over.
this is-
over round.
This is this line, right? Right? This is this line. Well, I mean, it doesn't look good. It doesn't look very good. But it's the line between x0, fx0, right? What is the slope of this line? The slope of this line is delta y over delta x, right? Right? Did we see this?
Yes.
This is how we motivate derivatives. And then this secant line, as I take h to 0, what will happen to it? It will become tangent line, right? This line that cuts, well, that joins two distinct points on the graph of y equal f of x. As x0 plus h approaches x0, or as h approaches 0, this tangent line, this secant line, this line between two points will become tangent to the curve, right? Y equal f of x at the point x0, fx0. Is that clear? Great. Now suppose I have a two-variable function. Okay, you've seen that derivative, right? You've seen this motivation for it. Now let's try to motivate partial derivatives in the same way. First of all, let's start by drawing some nice graphs in two variables. This is bad. I'm very bad at drawing, so you have to imagine it yourself. Okay, now let me take a point. Will this be very easy? Okay? Let's take fxy equal x squared plus y squared. Any volunteer to give me the first value of x? 1. A volunteer to give me a value of y? 3. So what is f1 3? f1 3 is equal to 10. So if I were to sketch z is equal fxy, if my x is 1, my y is 3, what would my z be? 10. Agree or not? So take x here, take y here, and take z here. What do we say? X is 1, y is 3, and z is 10. This is 1, 3, 10. Another point. What's the easier point? 0, 0. If x is 0, y is 0, what is z equal to? 0. We agree? Yes or no? If x is 1, y is 1, what is z? 2, right? X is 1, y is 1, so z is 2. Now, let's say if y is 1 and z is minus 1, what is, sorry, if y is 1 and x is minus 1, what is z? 2, right? Agree or not? So really, okay, this is another point. X is -1, y is 1, and z is 2. Notice that these are the same height, right? So your function looks something like this. And then you have, so, okay? Looks something like this. You see that? You guys see this? Z x squared plus y squared. So if your value x squared plus y squared is the same, your z value doesn't change. You agree with this? If 2 points in the xy plane have the same distance from the origin in the xy plane, then their z value under this function is the same. You agree? So these are just circles that you stack them up above each other. You see that or not? You guys see this? It's a these are circles that you stack them above each other. You see this? Like this, and the circles are of growing radii. That's a parable, okay, it's very hard to sketch these, but this is how, right? This is how it looks. Right? You see this? It's not a it's not very graphical, but this is how it looks. Okay. What do we call this? In the plane we call y equal f of x a curve. Here what do we call it? A
Plane.
surface. Z equal f x y is called the surface, or it's called the graph of f x y, but it's the surface. Y equal f of x. How many dimensions does the line have? Does the curve have? How many dimensions does it have? 1. How many dimensions does this one have? 2 dimensions. Right? How many unknown you need? How many parameters can you fix? You need to fix x and y, and z is given to you automatically by the rule fxy. So this is a kind of a 2-dimensional object. This table is a surface, right? What is the dimension of this? 2, right? Now say I lift this. I lift it this way. How many dimensions does this have? 2, right? This is my function. Z, x and y are on the bottom. It's a bit tiring, so I will drop it. But this is a 2-dimensional object. You agree with this or not? In how many ways can you parameterize this plane? A plane is, what is the dimension of a plane?
But isn't each circle 2D, and then when you put them on top, it becomes 3D?
The circle. You're talking about the disk. The disk is 2D. The circle is 1D. The circle is one line.
But the circle is like a plane.
The disk is in 2 dimensions.
Yeah. And then this thing is a
Yeah.
3D then, because it has like
The inside is not. The inside is not in the plane. Right?
Okay.
You see that? So take this.
Yeah.
Right? The inside of it is not the function. The function is just this boundary.
But doesn't it have length, width, and height?
Sure. So what is the dimension of a curve? The curve y equal f of x. What is the dimension of it? 1. But it still has x and y.
Okay.
Okay? But you need to know x, and then you can know y. Now take a plane in 3 dimensions. What is the dimension of a plane? So I have to tell you x plus y plus z is equal to 0. What is the dimension of this plane from linear algebra? 2, right? Because you take a basis for this vector space, you have 2 basis vectors, right? You have basis of size 2. You agree with this or not? Even though if you have 3 coordinates, but you kind of have 2 degrees, guys, please. If you have 2 degrees of freedom, you can choose x, you can choose y, and then z is automatically given to you. You're not free to choose z. You agree or not? If you have x plus y plus z is equal to 0. Are you free to choose z if you choose x and y? Z is given for you. Say you choose x and z. Are you free to choose y? No. Okay? So this is a 2-dimensional object. Okay? 2-dimensional object means that you haven't seen parameterizations, but we will see later maybe that you can parameterize it using 2 variables. A plane, how many variables can you parameterize it? You can parameterize it with 2, right? What do you need to parameterize a plane? 1 point? and two vectors that are not parallel, right? A line, what is the dimension of a line? Even in 3D, I'm in 3D now, what is the dimension of this line? 1. How many variables do you need to parameterize a line? 1. So you need a point and one parallel vector. Do you agree or not? Okay? So this thing is a two-dimensional object, even though it lives in 3D, just in the same way that the curve y equal f of x lives in a two-dimensional space, but it has dimension 1. It's just a line. Here is the surface. Okay. Now I will draw it another way now. And we'll try to motivate the derivative the same way as we did for the curve y equal f of x. You have a surface here. Z equal fxy. Yeah, I want to show it in a better way. Let's show you why. Okay? You have a surface Z equal fxy. You agree? Z equal fxy. Now I tell you, who wants to give me a number? Number? 4. And I tell you, fix y is equal to 4. You get fx4, isn't that right? Yes or no? Now z is equal to fx4, while y is remaining at 4. What is this? What is the curve z equal fx4? How many dimensions does it have? How many? 1, right? Once you choose x, z is given to you automatically, because I am fixing y. So really this is a function of how many variables? fx4 is a function of one variable. So I fixed my x is equal to 4. Now, in 3D, x equal to 4, what is it? What shape is this? X equal to 4 is a plane parallel to the yz plane, right? You've seen this before, no? X is equal to 4 is a plane parallel to the yz plane. So let's say this is the z-axis, and this is the y-axis. Okay? It's not intuitive, but this is the z-axis, and this is the y-axis. This is the plane x is equal to 1, right? You see that? So x is equal to 4 is a plane that is parallel to the yz plane, with the property that any point on this plane has the value x equals 4. You agree with this or not? The yz plane, how can you characterize it? What is an equation of the yz plane? X is 0, right? You see that or not? You see this or not? Linear algebra? So take the xy plane. What characterizes the xy plane in 3D? That their z value is equal to 0. Okay? So I take the plane x equal to 4. Now you know it will intersect the curve, it will intersect this surface at one curve. This is my surface. Okay? Anybody has a pair of scissors? Pair of scissors? Anybody? Okay. This is my surface. You have one?
I have a knife.
Okay. Okay. I mean, you know, I could do it here, but you know what? Let's not use. Let's try. Okay, now imagine this is one sheet of paper, okay? Imagine this is one sheet. Oh man, okay, it's gonna collapse. Okay, now it's harder. Anyways, okay, I just need anybody has a pen? A pen? Because I don't wanna, and it's hard to cut, I may cut myself with it, so scissors is easier. This is my curve. Z is fxy, okay? And let's look at this plane. This plane will cut my surface on a curve. So you go up, it will cut my surface on this curve. I mean, you see that or not?
Yeah.
You see this? You see what's happening? So you have your surface here. In 2D, in y equal f of x. So if y is a single variable, y is equal f of x. You have this curve, right? Set x equal to 1. Where will it cut the curve? It will cut it in 1 point. Here, if you say y equal to 4, say this is what the plane y equal to 4, it will cut my surface, just go up, okay? Go up, go up, go up, go up, and look at the intersection. It's going to be this curve. You see this? You see how it's happening? I mean, I could cut it, but yeah, no, this is difficult. But this is what's happening, really. Okay, so you're considering this one. It will cut my surface in one curve. Okay? Is it clear?
Yeah.
Great. Now this curve, I can represent it by a function, which is fx4. Y is fixed. X I get to choose. Once I choose x, y is 4 and fixed. What is determined to me? What is determined? What can I find immediately? Z. Do we agree with this? Do we agree? Should we do this again, or that's fine? It's fine? My demonstration, yeah. Okay. Thank you for the night. Yeah. Catch. No. Okay. Okay. I think I'll have to edit this from the. Anyway, okay. So you guys saw what's happening here. Once I fix y is equal to 4, once I fix say y is equal to, well, here I have x is equal. Well, here I have x is equal to 4. But anyway, here I fix x is equal to 4. Sorry. Here x is 4, so I have 4y. Okay. On the graph I have x is 4. Doesn't matter really, just a graph. Okay. So I have a function of one variable. Once you have a function of one variable, and you have the curve here, what can you do with this function? What can you draw for this function? Function of one variable, what can you do with it? Differentiate. What else can you do? Sure, integrate, very good. Limits, very good. Other than that, a curve. So when you have a curve, what can you do with a curve? What do you find for a y equal f of x? Slope of the
Tangent line.
tangent line. So here I have f4y. And how do you find the slope of the tangent line at a point here? What do? You differentiate with respect to y. Great. Now let me do the same thing if I choose y to be fixed. You can do the same thing if y is chosen to be fixed, right? I won't draw it because it's going to mess it up. But do you guys see what's happening? Okay. Now, so far so good. So far so good. Okay. Now if I were to fix this point, say, okay, x is equal to 4. So say x is equal to 4 here. So any point on this curve as x is equal to 4. If I tell you, and this is a point y, okay? What is the slope of the tangent line to this curve? At a point y, as x is equal to 4. If you set this to be g of y, what is the slope? It's just g prime of 4. You agree? X is fixed, but y is changing. You can differentiate with respect to y. Is it clear here? Are we good? Can you do the same reasoning with y being fixed but x is changing? Yeah. Okay? Are we good here? Okay. So we say fxy as a partial derivative, I don't know what the book calls it, with respect to x, or as the first partial derivative. It's weird they won't mention at the point 12 at xy if the limit as h approaches 0. Now I'm differentiating with respect to x. So x is varying, and what happens to y? It stays fixed. You guys see this? If I fix y is equal to 4, well, I mean that's it. Say I fix y is equal to 4. My curve will be z is equal a function of x. We agree or not? Yes or no? That's clear, right? And with respect to y, sorry, limit as h approaches 0 of f of x y plus h minus what? Minus. Anybody can help me here? What should I put? X, y. Okay, are we good here? Now, in terms of derivatives, what does this mean? It means differentiate with respect to x, while y is held constant. This derivative, this limit means differentiate with respect to y, while x is held constant. So, we denote I prefer this notation. F sub 1 of xy. This means derivative with respect to the first argument. Okay? There are other notations, but I'll try to stick to that. What do we have here? First argument. Okay? Sometimes, well, we also use f1 is equal fx and f2 is equal fy, but you should be careful here, okay? I'll explain why. You should be careful. Just in the same thing as one variable, so you should be careful, okay? Great. I mean, f sub y is really a function. It's not, okay? Anyways. Let's do an example here. What time is it? Anybody can help?
50 minutes left.
50 minutes left. Okay, 27? 37, okay. Great. So, of course, what do you expect about the partial derivatives? That you can add them up, right? You can add, because of the limit laws, if f is differentiable with respect to x and g is differentiable with respect to x, then f plus g is differentiable with respect to x, right? Okay, so find read it. Anything here is good. Let's see. Let's pick one. Someone give me a number. Number? Any number? Positive number? Integer? 5? Another number? 16. Another number? 9? Let's see. And one number from someone who hasn't spoken today? 7. Great. What is f1 xy? What is that? What do? We differentiate with respect to x. So what is held constant? Y. So whenever we have a y, you treat it as a constant. Great. So y to the 16, I can put it here immediately. I know I won't touch it. Agree or not? Great. So what do I have? I have x to the 5 times e to the x9 y to the 7. What rule do I use here? Product rule, right? Agree or not? So let's differentiate that. What is the root of x5? It's 5x4 times u prime v plus v prime u, right? So I put the u here, x5. What is v prime? I have to differentiate this and use the chain rule, right? If y is constant. So how do I differentiate this? It's 9x to the 8 times y to the 7 times e to the 9. Agree or not? Yes or no? Yeah? Did I differentiate this correctly or did I mess it up? I forgot y to the 7 here, right? Yeah. Is it clear or not? So I mean you can group them, so 9x to the 13, y to the 7. You see how to differentiate these? Everybody, are we good? We differentiate with respect to y. What do we get here? Are we good? Did I differentiate this correctly? Is it correct? Now let's differentiate with respect to y. What is that constant here? X. So I have x to the 5. Great. 16. So I have a product. So it's 16 y to the 15 times e x9 y to the 7 plus I have to differentiate e to the x9 y to the 7 with respect to y, while x is kept a constant. How do I do that? 7 y to the 6 times x to the 9 times e to the x9 y 7, and then I don't have to forget the y to the 16, right? . Agree or not? Is that good?
Yes.
Our derivative is good? Did you double check? Did I make a mistake? I could have easily made a mistake. Did I make a mistake? Did we differentiate? Is it good? Okay. So far so good. Great. Let's do some examples from the book. We do examples from the book. Usually there are numbers that are nicer than mine, so I'll stick to the book. Find x1 or fx xy and evaluate it at a given point. Fxy, well, this one is easy, so let's pick a harder one. X plus x squared. 2, 0. So what I want you to find is the derivative with respect to x and evaluate it at the points. Like that. Over here. Because I want the derivative at the point. So how do you differentiate this one with respect to x? What is fx xy in that case? Who wants to help me? Help? Help,
Y
help,
plus
help.
2x.
What is it?
Y plus 2x.
Y plus 2x, very good. Now we evaluate it at the point 2, 0. What do you get?
2, 4.
Let's do one more. Oh, we do a harder one? Let's do a harder one. Arctan y over x, and I want you to find fx. I mean, it's in the book, so I hope they have a nice value. I think they do. X minus 1, 1. That's a nice one. So, what do I have to differentiate? I have to differentiate arctan y over x with respect to x. This means that my y is held constant, right? So I treat my y as constant. Great. How do I differentiate this? How do I differentiate this? Any volunteer? I treat my y as constant, right? So whenever you have y, you just treat it as constant. F1 xy. What is this? I differentiate y over x with respect to x. I remember that y is a constant. What is the derivative? It's minus y over x squared, right? The derivative of arctan. What is the derivative of arctan? 1 plus 1 over. So what do you get? You get minus y over x squared plus y squared. Do we agree with this or not? Everybody, do we agree? 100%? Is it clear? Why you treat it as a? Is it good? You treat y as a constant. Is it clear or not? Okay, let's evaluate this at minus 1, 1. What do we get? X is minus 1 and y is 1. So I get minus 1 over 2, right? We do more? Should you do more of these or not? I mean, really what you're doing here is a chain rule, right? You're really doing the chain rule. I mean, I will write it here later, but this is the whole thing. But I want you just to see that this is just a problem in one variable. You agree with this? Let's do one more. We do a harder one or an easier one? Let's do a harder one. Let's do a harder one. Let's see. Well, yeah, I think this was the. Well, I mean, let's do another one. Or do you want to do fy f2 here? Let's do f2. What is the derivative with respect to x here? What is the derivative with respect to y? Let's do f2. I mean, I deviated from the question, but that's okay. What's the derivative with respect to y? With respect to the second argument, what's its derivative?
1 over x.
Exactly. Very good. Do we see that or not? X is held fixed. Okay? X is a fixed number. You have to differentiate y over x with respect to y. What is the derivative of y over x with respect to y? 1 over x, right? Now, again, x is held fixed. So, but I mean, it's the same thing here, right? It's a chain rule. So what do you get? You get x over x squared plus y squared. Is that right? Let's see. Okay? Are we good here? Are we good? Now fxy, sine x root y. How do I differentiate this? I want to differentiate this with respect to x, say. What is held constant? Y. How do I differentiate this with respect to x? So, yeah, so what's the first thing to do? So say you have sine x root 10, for example. How will you differentiate this? You take the root 10 out, right? X root 10 with respect to x, so it's root 10. What's the derivative of sine? Cos x root 10, right? We see that? Yeah, we see this or not? Yes or no? Yeah, I just differentiate it the same way. So it's root y cos of x root y. What's the derivative with respect to y? It's a more interesting derivative with respect to y. So, if I differentiate with respect to y, what is held constant? X. So, sine x root y, what do? I take the term inside and differentiate with respect to y, while keeping x constant. What do I get? X over 2 root y, right? We see that? So I get x over 2 root y. What's the derivative of sine here? Cosine x root y. Okay? Are we good here? Are we good? Should we do more? We do more derivatives or that's fine? Let's do more. Let's do more. Let's do more. Let's do more. Let's see if I have a nice one. I don't think there's I don't know. No, I didn't put this into work. Work 3 is then, did I put this into, I don't know. Work 3 I think is in your algebra. So just to make sure that it's in your algebra. because we're gonna need it after.
When we're prepared.
This is gonna be what we're for, yeah. This is our release time. Okay, should we do something slightly harder? Could we do something slightly harder?
Yes.
I mean, I did not like really explain this in detail, but we could do this very easily. Okay? If you can just do your intuition, then that's gonna be fine. So let f be a function from R to R. Be differential, okay? I mean, that's what you have been doing. You have been doing this all along, okay? And I can let gxy be equal to f of x squared. Let's see, what do they have here? X squared minus y squared. Let's give ourselves an example. Who wants to pick their favorite function? Who picks their favorite? Someone pick their favorite function. Interesting function. What is it? An interesting function. Cos, arcsine, arccos, arctan. No, that's not the case. But let's pick something. Cos, for example. Okay. Okay, let's keep an analogy here. I want to differentiate this with respect to x. What do you do here? Always look at here. X is constant. Y is constant and x is a variable. How would you do it here? X is a variable and y is constant. How would you do it?
X is constant.
X is a variable. Differentiate with respect to x. I want g sub x. 2x times
2x minus y, x squared minus y squared.
Do we agree or not? How would you differentiate this? If y is to be held constant, say y is 1, how would you differentiate this?
2x and negative 2x sine x squared minus y squared.
Very good. Do we agree with this? Very good as well. Do we agree or not? Everybody, do we agree? If y to be held constant, then this derivative is 2x minus sine x squared minus y squared. Now, what is the derivative of this with respect to x? Y is held constant. What do you do here? Yeah, what do you do? I just replaced f by cos here, right? What did you do here? Is that I differentiate the inside with respect to x, right? You agree? And then what do you say? I take the derivative of cos, which is minus sine, and I apply it to the inside. What would happen here? So 2x times the derivative of f, very good, f prime, applied where? Differentiate, so you want to differentiate the inside, right, with respect to x?
Yes.
Y is constant. What happens? Okay, say y is 1. You want to differentiate fx squared minus 1. What happens? 2x f prime of x squared minus 1. Do we agree with this or not? Everybody, do we agree?
Wait, can you please explain that last part?
The last part where? The f prime?
Yeah.
You're looking at this as a function of technically one variable, right? Because y is held
Constant.
to constant. Differentiate this with respect to x. Suppose you had fx squared minus 1. Differentiate this with respect to x. What do you get?
2x.
F prime of x squared minus 1. Y is a constant, an arbitrary, a constant. How do you do this if you want to differentiate with respect to x?
2x.
Are we good here? 100%? You're gonna have something like that on your midterm, okay? Something like that, easy, just to check that, you were following and, alive in the course. That's what I want. Okay, you're gonna get something easy like this. I think it's worth 10 points, I think. A question like this is worth 10 points.
On the midterm?
Yeah.
10 points over what?
Over, I think I put 50 points. 50 points. 50 points, 50 minutes. Each minute 1 point. So no, I think I put it on 20. So I think I wanted to put it on 25. But on 25, I think I tend to be meaner in grading. So I remove 1 point, right? So instead of removing 1 point on 25, I'll remove 1 point on 50. Right? Because usually it's by mistake. Right? You remove 1 point if you made a mistake. Nobody count. Usually I don't count, how. So I remove 1 on 50. So it's in your benefit actually.
How many questions is the midterm?
Pardon me?
How many questions is the midterm?
I said I think it's 4, no?
4 or 5?
4 or 5? Well, 5? 5. What did I say? So the first question is series, converge absolutely, conditionally, or diverges. The second question, interval of convergence.
And radius of convergence?
One of these, like both, maybe one, anything. So radius or interval, for which values of x does this converge? And then the third question is like find the 79th derivative basically in each of the cases, and using power series basically. I mean, I'm telling you the questions. I just want you to do well at this. The final is gonna be totally different, like something totally different, but you will be ready. Okay. And then the fourth question is something like this: differentiate. A thing you get, in your first calc 1 exam, you get a derivative of polynomial basically, right? So it's something like this here. It's an easy question.
And what's the grading for each question? Like 15 to 10?
I think the series is on. So to my memory, 20, 10, 30. 10, 10. So like each series, you have 4 series, each worth 5 marks, and then, but don't hold me accountable for this. This is just pure memory. So 4 series worth 5 marks each. Then the second exercise, radius of convergence, is worth 10 marks. You have 2 of them, 5 marks each. And then what? The 79th derivative, or I don't know what, you have 2 of them, 5 marks each. And the question on partial differentiation is 10 marks. Okay, 10 marks, 3 lines basically. It's gonna be, okay, so please do study for your picture. Okay, don't mess it up. Okay, it's gonna be a very nice boost to your grade. And getting 100, getting 50 on 50 is more than achievable. Getting 50 on 50, if you studied everything, you should be able to get 50 on 50 and ace it. So I'm personally not very worried about the midterm. The final will be harder. Okay, the final is going to be way harder than the midterm. Okay? Great. How much time do we have left? Are we done? 20 minutes, 25 minutes. Okay, great. Let's do one more. Okay, square root. Okay, let's differentiate this with yes, sir. Pardon me? Yeah, I think they're similar to what works and to the stuff we did in class. Okay? Again, I'm not gonna bring you something that you haven't seen. Okay, and maybe some of them are examples we exactly did in class. Okay, to my memory, like it's not because a lot of the time I just give examples like that, and usually these examples, when I write the midterm, they come up again. So it's going to be something very similar to what we have done in class. And know your limits. You know, sine x over x as x goes to 0. What is that equal to? 1. Limit of what's another one? 1 plus 1 over x to the x as x goes to infinity. What is that? E to the x. Okay, things like that you should know. For example, the limit of e to the x minus 1 over x as x approaches 0. What is that? Yeah, that's right. 1. Yep. Things like that you have seen. So the limit of cos x minus, okay, so cos x minus 1 over x, this is 0. So limits like that you should be able to know, okay? Plus 1 limits you should be able to know. Yes, sir?
You say the final will be harder because the option is 1 or 0, or
I think it's going to be harder than the midterm.
like even the midterm question, like the midterm material will be harder on the final.
Well, I don't think I will do a lot of, series you're going to have on the final. But for example, the series question on the final will be hard. Yeah, that's what you're asking. Yeah, the series question on the final will be hard. Yeah. Yes.
And could you provide a list of limits we need to know for the midterm question? Like what you mentioned.
Calc one. Just calc one limits. Okay?
Give us a list.
Yeah, I didn't call.
You know derivatives?
Yeah.
Okay. Yes.
For the small angle approximation for cos x, do you want us to do 1 or 1 minus x squared over 1 plus x squared?
Did I ever do a small angle approximation in class?
No, but we did sin x over x.
Yeah, but did I ever use a small angle approximation? No, I didn't.
Maybe I used the wrong name, but
No, like series, you mean, the series of sin x.
yeah.
That you need to know, yes.
Okay.
Okay? But
But if we get like the limit of x goes to 0, I forgot what that x is.
of what? Of sin x over x is 1.
And then what's the cosine?
Cosine x minus 1 over x is 0.
Oh.
You can do this using series, for example. Okay? You're not gonna get something we haven't seen in class. But you're not gonna get something out of this room. On the final, you're not gonna get this either. But the problems are just gonna be tough. Okay? Yes. What is? I have no clue. So usually it's either third or fourth. That's what I've been told, but I have no clue on the time nor on the date. Great. Let's differentiate this. And I think you should do the quiz, because the quiz is going to be a sample midterm, okay? Like, it's just going to be a sample midterm. The quiz that I will post is going to be a sample midterm. So, like, don't just chat GPT it, okay? If you chat GPT it, you'll probably get the answer. But I think it's a wise idea to sit down, time yourself for 50 minutes, study. First of all, study. Time yourself for 50 minutes, and then do it. Okay? Yeah, it's going to be very, it's not going to be terrible. And I think it's better this way, you know, it's really better this way, that you do well on the thing before the midterm. You ensure that you're in good shape, you know, doing well in the class. And then the final, you need, if say you get 50 on 50 on everything, you need to score 70% on the final to get an A. Usually it's achievable. Usually I make it reasonable to get 70%. 85 and above, it becomes a bit harder. But, which is fair, I think. I hope so, at least. Great. Let's do this. But again, you study, you get the marks. You don't study, good luck. Okay? fxy is root 1 plus x cubed. I mean, it's like that. Well, I mean, it's better than all your courses, right? Because some courses you study and you don't do well. Okay? In this case, it won't happen. If you study, you ensure 50 on 50 on everything before the midterm, and then it's very reasonable to achieve an A if you just work hard. Getting an A is very reasonable. As you see, I'm giving you a lot of work, and a lot of it is repetition. You just stay and you're comfortable in doing this. So that's what I want. Anyway, enough talking. Let's do this. How I differentiate this with respect to x? What is held fixed here? Y. So what do? I take derivative of x cubed y squared plus x by x. 3x squared y squared. Then what happens to the roots? Agree? Yeah? Agree or not?
Yes.
Derivative with respect to y, what is the derivative with respect to y? It's 2y x cubed, right? Divided by the same stuff. Okay, great. We still have 10 minutes left. We still have 10 minutes. 15, 20. Okay. So let's do some tangent lines. So let's do a tangent plane stuff. Okay? It's good. We're gonna end with pictures now. We're not gonna do lots of math. We're just gonna end with some pictures to derive the equation of a tangent plane. So in the curve y equal f of x, what did we do? We took the derivative and we saw that the line is tangent to the curve, right? Yeah? Okay, now we're going to do the same reasoning, but for a surface. The surface will not have a tangent line, but will have a tangent plane, because there is kind of 2D, right? If you look at here, for example, right? This is a surface. And you want to look the tangent at this point, right? You may have a lot of tangents. So this line is tangent, this line is tangent, this line is tangent, this line is tangent. So, but those tangent lines lie in one plane, right? So let's try to derive the equation of this plane and see how to derive it. We're going to get back to the pictures we have drawn before. I have x here, I have y here, and I have z. And I have the surface z is equal to fxy. And pick the point AB. So x is equal to A, and y is equal to B. Well, I need to work on my drawing skills a bit, but we'll just deal with that later. So I have x is equal to A, and y is equal to B. And you look at this point, right? You get the point here, and then you get the z value there. Agree or not? This is the point. I want to find the tangent plane at this point. Now, to find a plane, what do I need? What do you need to find a plane? How do you find a plane in linear algebra? How did you find the equation of a plane? So someone who hasn't spoken today, what did you do to find the equation of a plane? What did you need? Please raise your hand. Linear algebra, math 133. What did you need for a tangent plane? For a plane, sorry. How could you find the equation of a plane? Yes? Normal vector and a point. Very good. What's something else we can do? To get a normal vector, what can you get? Very good. That's a very good answer. To get a normal vector, what if I don't give you a normal vector, for example? That's something. So you need one normal vector and a point. We'll use that. Yes? Two lines in the plane, very good. But what can I say? What should those lines be? How should those lines be? Yes? Non-parallel, right? So if you give me two non-parallel lines, I can find a normal vector. How do I find a normal vector from these non-parallel lines? Cross product. Awesome. So I have two non-parallel lines and a normal vector, which becomes of the cross product of the two vectors, non-parallel, and then I get an equation of the plane. Is that okay? Great. That's what we're going to do now. We're going to try to find two tangent lines to this surface at this point, and then take their cross product to obtain a normal vector, and then derive the equation of the tangent plane. So I have my x equal A and y equal B. Now I have xy. Now let me fix b. Let me fix y. Or what do you want to fix? Let's fix x. And I consider this curve. Agreed? This function. f a y. X is fixed, but y is variable. This curve is, so x is equal to a. This curve is here. Do you agree or not? Let's do this. X is a. This is the curve I get here. It's a function of how many variables f a y if x is fixed. One variable. So, sorry, if x is fixed. It's one variable. So I can find the tangent line to this curve when y is equal to b. Agree or not? Yes or no? What is the slope of the tangent line? At the curve f a y when y is equal to b. What is the slope of the tangent line? You have to be a bit careful here.
Y over n.
Y over? Y over n.
For n.
Y, well, you're meaning the depends on the derivative, right? Yeah. But what is it then? F? Yeah. F? Well, what's f prime here? Exactly. So what did we call it? F sub y or f sub
F sub
2 AB, right? What is the slope of the tangent line at the point AB here? It's f sub 2 AB, derivative of f with respect to y. When you plug in y equal b. Agree or not?
Yes.
Everybody. So the slope of the tangent line is f2 AB, right? What is the equation of the tangent line in this case? I need to parameterize it. Yes, so what is the x value in that case? X is equal to a. Let's say y is equal to t. And that will be equal to f2 ab g. What is that? So what's the equation? This is z f prime of a times x minus a plus f of a. Agree or not? This is in one dimension. Now, you have z is equal to fay. This is the curve that you have in 3D. What's the derivative of the plane? What's the tangent line to this curve at this point? This is just f2 AB, right? Yes or no?
Could you please re-explain the part with
Yeah, no, I have something to do. I have something to complete. So it's not done. Okay? So x is equal to a. What is the derivative of this line? Times y minus b. Right? Plus f(a). Agreed? This is a curve. This is a line in this plane. Now, is this enough to characterize a line? This is a plane, technically. And then you impose x is equal to a. You agree with this or not? You agree with this? What is this curve? This is a curve of one function of one variable. Agree? Z is equal fay. How do you find the tangent plane, tangent line to the curve?
That is just this curve?
Yeah, this is this curve here.
Okay.
How do you find the equation of this tangent to this curve when y is equal to b? You differentiate with respect to y, you plug in b, then times y minus b plus fab. One variable, this is one variable, right? You're just plugging y for b. B for y, sorry, right? Great. So what is this equation? So y is equal to b plus t. Well, what we can choose y is equal, let's say, y is equal to b plus t, right? And z will be equal to f2ab, y minus b, which is t, plus fab. Let me write another way. Let me write the fab here. Plug in t equals 0. What do you get? You get ab fab, right? Does this point belong to the tangent? Does this point belong to this curve? Yeah, which is fine. Okay? This is a check. Now, what's a vector parallel to this line? How do you find a parallel vector to this line? This is a plus 0t. What's a parallel vector? 0, 1, f2, ab. A parallel vector to this line is t1, 0, 1, f2, ab. I'm not in the book if I do it this way, but oh yeah, I can do it this way. Okay, nice. Okay? Are we good here? Yes.
Before we move on, can you please explain how you got the equations for y and t?
Here?
Yeah.
Here, this is in one variable, right?
Yeah.
In one variable, that's what you have.
Okay.
Okay? Now, you have a curve, z is equal fay.
Yeah.
When you fix x is equal to a.
Yeah.
What is the tangent line to this curve, to this one-dimensional object, when y is equal to b? You differentiate f with respect to the second argument. You plug in b,
Yeah.
right?
Yeah.
Times y minus b, because y is the variable here.
But why are you doing y minus b there and x minus a there?
No, this is in the plane.
Is this a tangent line approximation thing?
Yeah, this is the tangent line equation of y equal f of x and x equal a.
Well, I didn't learn that.
Okay. You didn't see this in Sat 1?
I was exempted.
Oh, okay. Well, this is the equation of the tangent line when y is equal to b.
What's the general formula for the tangent line approximation?
Equation of tangent line. No? F prime, so if you have y is equal to f of x, at x is equal to a, this is just f prime of a times x minus a. Plus f of a, right?
Oh wait, is it like y is m x?
Sure, m is f prime of a, b is minus a f prime of a plus f of a, if you have seen it this way. Or sometimes you find f prime of a, you plug in the numbers, right?
Yeah.
So you need the slope. The slope is f prime of a, and you need the point on the line, a f of a. Okay, plug in x. Okay. Yeah.
Okay, so I understood the 1D.
Yeah.
Now for the 2D, it's the
Here.
same thing. Okay.
Here is the same thing, but z is just a function of y.
Okay.
So this is the tangent line.
Thank you so much.
No problem. This is the vector that is parallel to this line. Agreed? So I kind of find a line, a vector that is tangent to this surface at this point. Now, what if I do the same thing? What if I fix, the same thing but in a different way. I fix y is equal to b. This is my point AB here. And this is the point y is equal to b. I get a different curve here. Agree or not? What is the function? What is the curve? How could I call this curve? If y is equal to b, let me write here. If y is equal to b, my curve becomes z is equal to f xb, right? I'm fixing y to be equal to b. Agreed? This is my curve here, and I can parameterize it by fxb. This becomes my function. You fix y is equal to b. Now, I'm looking at the point AB. What is my value of x I'm interested in here? A. We agree or not? Everybody? Everybody, do we agree? I'm interested at the point AB. What is the tangent line for this curve when x is equal to a? Is it z? F, the derivative of f with respect to x when x is equal to a. So apply or evaluate at x is equal to a, f1a, x minus a plus fab. Agreed? This is a tangent line. How do I parameterize this line? Y is equal to b, right? And what is x? X is equal to a plus t. And z will be equal to f1 ab times t times x minus a, which is t, plus fab. What's the perpendicular parallel vector to this line, sorry? What's the parallel vector to this line? So here I have a tangent here, and I have a tangent here. What's the parallel vector to this line? How would you read out the parallel vector to this line? You look at the coefficients of the parameter, right? It's 1, 0, f1 of ab. So I have two vectors that are tangent to the surface at the point AB. Are these vectors parallel or not? Are they parallel? They're not parallel. You see that?
No, they're not.
They're not parallel. How do I find the normal to the plane? What do I take?
Cross product.
The cross product. Okay? So T1 cross T2. What do I do? I, J, K. So what do you get here? F1 EB. Then dot F2 AB, right? And then what do you get? Minus 1. What's the normal vector to the plane? What's the normal vector to the surface at the point AB? Or a normal vector to the tangent plane to the surface at the point AB? It's this vector. How do I find the tangent plane? Tangent plane to Z is equal fxy at AB, sorry. Just please one minute, and then we'll finish. If I give you a normal vector, how do I find the tangent plane? It's just f1 AB times x minus a, right? Because it goes through the point AB, f of AB plus f2 AB y minus b, right? Plus or minus z minus fab is equal to 0, or if you wish to write it in a better way, then okay. Do you understand what happened? How we derive this plane? You don't need to know the derivation, you just need to know the result. Okay, is it clear how we derive this? You look at the curve, you fix x is equal to a, and you let y vary, you find the tangent line. Now you fix y and you let x vary, you find a tangent line. Now these two tangent lines will not be parallel to each other, and they will generate a plane. You find the tangent plane. Okay? Great.